he promised that he will watch the video, so let's do a good job. So this is a joint work with the team G's. And that's the title, locally free holomorphic actions of the complex affine group. So this work is motivated in fact by Etienne's thesis in 1979. Had the good fortune of knowing him at that time. And he studied the following problem for the real case. So he considered the real affine group is simply the group of affine transformations from the real line, proper affine transformation of the real line. So in fact, in this case, the affine group is an extension. Is it unique? So I will denote by that this group. The real affine group is in fact an extension of the unique solvable group. The unique non-trivial simply connected Lie group of dimension 2, which is not a Lie group. And the problem he solved is the following. So I state the theorem. Let C be a locally free C2 action of the real affine group on M3. So it's a compact, connected and closely manifold. Of course, group manifold. And here is a hypothesis that looks very restrictive, but in fact it's not. There's an idea that maybe it can be dropped, which preserves C0 volume form. That's the hypothesis. Okay, so it's a real three-dimensional manifold. You have a locally free. Of course, locally free means that the stabilizers of every point is discrete, as usual. The isotropy subgroup for every point is discrete. And then this implies a remarkable fact of rigidity. It implies the action is rigid and homogeneous. The action is homogeneous. So it's remarkable. Yeah, just this hypothesis implies rigidity. Unique way to construct these examples. So what does that mean, homogeneous? It means that the manifold M is a homogeneous manifold Right. Put it another way, that means there exists G simply connected Lie group of dimension 3, real dimension 3, which contains the affine group as a subgroup. And the lattice, well, more than lattice, a co-compact discrete subgroup gamma, such that the manifold M, I'm a little bit dyslexic, so be careful with left and right opposites, maybe I made a mistake. The manifold M is obtained by quotient this discrete subgroup, and such that the action so of course the affine group being a subgroup of that acts on left cosets by right multiplication. So this affine group, the action of F real is by right multiplication on left cosets. And this action is exactly infinity conjugate to the original one. This action is infinity conjugate to the given one. And furthermore, immediately the action will preserve Hermitian. Well, more precisely, Hermitian induced in the quotient. Okay, so in fact, in this case, the infinity volume form is replaced by a real analytic volume form. Now here, therefore, everything is reduced to study three-dimensional Lie groups that contain a affine group and lattices, and that's well known, and can be divided into two.
It was C0.
C0. The volume form is C0. So you only, but it has to be not any measure. I mean, of course, these things always preserve measure, because I remind you that a affine group being solvable is an extension of R by R, is automatically amenable, and so we'll leave an invariant measure. But we want this measure to be actually not only having support the whole manifold, but actually given by a continuous volume form. So it's rather restricted, but I will say a word about it. And in fact, therefore, everything is reduced to studying the couples consisting of a G and, well, actually, G being simply connected, G is of two types. So there's a dichotomy. There are two possibilities for G. Well, the first standard is G is the universal covering of SL2R, which certainly contains the affine group as a subgroup, or else G, so this we call the semi-simple case, or else G is solvable, so we call the solvable case, and G is exactly the following form, semi-direct product of R2 with R, solvable case, right? And it's actually a semi-direct product, a speed extension given by some map. Well, this therefore is exponentials given by holomorphisms that determine the semi-direct product is given by a certain matrix like that. That's the way you twist the semi-direct product. So there is a complete dichotomy, and gamma. We only therefore have to show the existence of such gammas, and this is a well-known case because gamma exists. For instance, example, the fundamental group. Well, actually, a central extension. But I maybe drop the bar for a moment. There's ambiguity. The integers, but I don't care for the moment. Example, the fundamental group of any surface or genus well, an extension of that for genus G greater or equal to 2 is such an example, because I remind you that the unitangent bundle of any such surface is always of the type, well, actually, PSL2R divided by gamma. So, this is one case. And this solvable case is extremely interesting also. The lattices for this case correspond to the following object. So here will be a lattice of R2, namely lambda. Not here, as a lattice isomorphic to Z plus Z. Here gamma, here Z, here 0. So the fundamental group is therefore an extension of the free abelian group to be generated by Z. This enters as a lattice here, and this enters here. And the manifold obtained that way can be better described geometrically the following way. You take the torus, T2, multiply by the interval. So schematically is like that. And then glue the left with the right by automorphism of the torus. For instance, the classical example would be one of the most favorite matrices, I suppose, in this place. Or as a matter of fact, any matrix which belongs to SL to Z. Well, this is an example of what is called a mapping torus, right? This has a canonical flow. The only condition for having the only problem is that this group G must contain the affine group as a subgroup, and this amounts to the fact that the gluing matrix must have a eigenvalue different from 1. And it's the only condition that we must have for G contain the affine group as a subgroup. So this has a complete list of, just a parenthesis, I learned something beautiful is that this example here, these manifolds are usually called 1 to be tori of dimension 3. They are not, they fiber over the circle with fiber the torus, but there's a monodromy, and the monodromy is exactly this gluing matrix. And therefore it's called T3 notation, new notation is T3A, where A is this gluing matrix. If A is the identity, of course, it's standard torus. But I mean, the parenthesis I want to say is that Poincaré invented the fundamental group precisely through this example. I was very satisfied because I'm an Anosov man, because this is an example of the suspension of an Anosov diffeomorphism. And I was very pleased to, I always thought that Anosov diffeomorphs were there in the corner of a corner of a corner of mathematics. I was very happy to know that Poincaré invented the fundamental group exactly for this example, because he noticed that for different matrices, the homology of this is in general depending on A. If identity minus A is invertible, this is always of the type Z plus torsion. So that's the way Poincaré was able to determine two three-dimensional manifolds that have the same homology but are not diffeomorphic. And Poincaré asked himself how to prove they are not diffeomorphic. Well, you take a point, then you take a curve, the family of homotopy classes of curves, you compose them, and he invented the fundamental group precisely for this example, which is really beautiful. Okay, so this gives you a complete list of functions. Now, regarding the condition of preserving a C0 form, the existence of such a form can be written in terms of a cocycle with values in the reals, and therefore, for instance, if the first homology group of the manifold, the real coefficient, is 0, it's a real homology sphere, then it's always possible to find a form class is 0, which is preserved by the action of the affine group. So you see, in a sense, it's to be expected that this is always the case, but still. So it's a very remarkable theorem of rigidity. Simple condition implies that you know all the cases of the action. And so the purpose of the talk is to see how far we can push this theorem for the complex case. So now, therefore, we must start.
Excuse me, how numerous are such three manifolds?
These manifolds are in one-to-one correspondence with SL to Z.
Oh, no, not these, but the ones that satisfy this homology condition.
Yes, and I give you a list of infinitely many. Okay, it's the following. It's actually a very good question, because
the examples that you gave us, of course, have non-zero homology.
No, exactly. They are said. But let me, and even the unitangent bundle, they are never. But now, if you take So everything is connected in mathematics. So you take the Briskow manifold, VPQR.
Oh, so we're getting to the subject of the talk already.
So, excuse me?
You're getting into complex stuff already.
That's right. That's right. But then it will be real very, very quickly. So you take the set of all triples of all points of C3, which satisfy this algebraic equation. So it's a singular manifold, well, you know very well, of complex dimension 2, but singular only at the origin, gradient dimension only at the origin. And you intersect that with the unit sphere S5. It will be transverse because it's a quasi-homogeneous function, so it's a cone, well, twisted cone. But, okay, so you intersect this object with S5, and you get a three-dimensional manifold, which is called VPQR. And as long as PQR are relatively prime, by each pair is relatively prime, and in the hyperbolic condition 1 over P plus 1 over Q plus 1 over R, if they are relatively prime, Briskow proved that it's actually a homology sphere. The PQR is a homology sphere. And as long as this condition is satisfied, it comes from a triangle group. In fact, it comes from hyperbolic geometry. And there's a theorem by Milnor and Rolkachev that says that in fact these manifolds are really beautiful because they are homogeneous. VPQR are always SL to R, universal covering, divided by a triangular group. So this gives you at least an infinite number of manifolds that have vanishing homology group. And it's an extremely interesting question because you see this Lie group, the Lie algebra, therefore is three-dimensional, has three generators which correspond to matrices of trace 0. So matrices of trace 0 are generated by these three ones. This will play the role of sort of a geodesic flow, these two holocyclic flows. And therefore you have three vector fields, x, y, z, left invariant vector fields that descend to this manifold, and therefore this manifold dimension 3, is provided with three vector fields satisfying the commutative relations is the Lie algebra of the affine group. And it's easy to see, not difficult to see, that the flows generated by Y and Z are minimal. So you have these three homology manifolds filled with a bobbin of curves which are dense. And therefore this is a famous conjecture, but I'm changing a little bit. You're sorti de la partition. These manifolds are homology manifolds that contain minimal flows. Orbits are everywhere dense. And there's this famous conjecture by Gottschalk saying that S3 should not have a minimal flow. I mean, the recent spectacular results by Kuperbeck say that you have counterexample to this type of conjecture. Meaning that you cannot use any argument which is only on homological. There's infinitely many examples of homology tree spheres that contain minimal flows. So no way to. And I know that by heart because once I used a homological argument, and I was writing a letter to Schweitzer, and then in particular examples of this. Stop my letter and wrote a paper. That's a counterexample to what I was saying. Okay, but okay. So this is a very rich theory. Particularly regarding these three vectors here, means that Y and Z determine a plane field, which is contact field. So this three-dimensional manifold is a circle bundle over a surface, over an orbital. This has arithmetic. If you take gamma to be an arithmetic group, has arithmetic, has ergodic theory, has minimal flows, has Lie group representation, has Sometimes it looks like all mathematics converge to these examples. Okay, but the idea therefore is to obtain a complex version of that one, this theory. Okay, so let me just point out that the idea is to prove this theorem based everything in the theory of foliations, co-dimension 1 foliation was extensively developed. Okay, now if I want to do the same thing, I would be in trouble because now will be real co-dimension 2, and there are not too many theorems of that. So, but to compensate, we have complex analysis, and that will be a way of compensating the fact that we know very little about foliations of higher co-dimension. So let me first point out what we want to do, what are the problems, how to complexify this. So the first problem, small, not problem, but small observation, is that now I want to study the group complex affine. And that, of course, consists of the complex transformations of the complex line. I is a non-zero complex number, or the group of complex automorphism of real line. Well, we see now that this group now is therefore still solvable, complex solvable. But now, so as a manifold, as a complex manifold, is C cross C star, but with a sort of twisted group structure, and it's not simply connected. So that's the first problem. And in fact, you can take, so the fundamental group is Z, you can take all the cyclic covering. So let me just write for you the loss of multiplication. So you define if K is an integer, well, you can define the cyclic covering. So I will suppress the C for the moment. It's understood that it's a complex thing that we are. So this consists of all couples A, B. With the law of multiplication of semi-direct product as follows: AB times. Here I'm a little dyslexic, so let me copy directly. Okay. Of course, if K equals, so this is the law of multiplication, semi-direct product. And of course, if K is equal to 1, it's exactly the affine group. And if K is equal to infinity, by definition, will be the universal covering of the affine group. So, in fact, we take the universal covering of the complex affine group. So, it will be an extension of this type. Okay, and the law of multiplication is now the following: alpha b times alpha prime beta prime. So it's additive now. Okay, we have this. So this is the complex affine group, already has small complication. They're not. There are several couplings in this group. Okay. And why do I bother to mention that? Is because we will study these actions via the Lie algebra, the infinitesimal generation, and I mean by that a real 6-form, no holomorphic context. Okay? In fact, I will explain a little bit more. So this is the problem. Can we classify them? Is there the same rigidity phenomena happening as in the case with the THGs? Well, the first thing to ask is if there are examples of that. Okay? Because, and there are examples, and in fact, the theorem will, the answer to that problem will be, all examples are the following that I'm going to give, in the same way as the case of Etienne. Well, of course, if we have SL to R, now we take, so now we take SL to C, which of course simply connected. Okay? So let SL to C, let gamma be a compact discrete subgroup. Of course, now we take left posits, and the affine group acts by random multiplication of left posits. And of course, SL2C contains, but here is a subgroup. There's an injection, not, you know, one tends to be sloppy when there's discrete ambiguity, you know, like spinors. So now there's a canonical embedding of the double cover of the affine group, not the affine group, into SL2C, which is explicitly given in the following way, AP. Like that. And on the other hand, there's a canonical embedding of the affine group into Web's transformations, those one takes in infinity as fractional linear transformation, that's written explicitly in the following way. So this is given the embedding of, of the affine group into PSL2C. SL2C divided by identity times identity equals Web's transformation of the complex Riemann sphere, and the embedding is explicitly given like that. And from these examples to these examples, we go via double covering, provided you can do it, and that's a condition on the second people read in class, that doesn't matter. So, another example, well, there's a theorem of Borel saying that yes, but actually there's a more intelligent, more concrete way to do it, is by recalling that PSL2C is exactly the same thing as a group of orientation-preserving isometries of hyperbolic space. Because any Möbius transformation from the Riemann sphere is a conformal mapping, has a unique conformal extension, and preserves the Poincaré metric in the inside. The Poincaré metric is the standard one, a 4, sorry. I always forget the 4. But like that. And so the only thing that, and of course it's more interesting because PSL2C is what? It's exactly the same thing as the frame bundle F of hyperbolic space. The frame bundle consists of 4 orthonormal hyperbolic metric frames anchored at every point. And of course this is true because if you give me any frame anchored at any interior point, at any point of the hyperbolic space and given any other oriented base, there's a unique hyperbolic isometry that takes this point to this point, and the differential takes this frame to that frame, and therefore that sets up a one-to-one correspondence. Is the same thing, right? And therefore the groups gamma are in one-to-one correspondence, in fact, with fundamental groups of hyperbolic orbitals. So we have as many gammas. So for each compact hyperbolic three-dimensional orbital, we have a gamma. The fundamental group in the orbital sense. So every time we have that, we have an action of the affine group on a complex. This is a complex D group of dimension 3. We divide by a discrete subgroup, we obtain a compact complex manifold which contains the affine group and the natural action of the affine group, and we recover therefore for each object like that. But this is already very interesting because, okay, before doing that, let me, now is there an, remember here I constructed the T3A. Is there a complex analog of that? Remember that these T3A in the real case were manifolds that fiber over the circle with fiber the torus, real torus. So the complex analog would be what? Would be a complex manifold fibering over an elliptic curve with fiber complex torus. Right? Is the analog of complex analog. And therefore, we have to do something which is we will call the holomorphic suspension. So let's call that. And of course, the theorem will say that all examples are in the list I'm going to give, provided there's a measure you are voting for, which is preserved. Okay, so first recall that the suspension is the following. So if F is a diffeomorphism, C infinity, and N is a compact manifold, then there's a canonical way to construct a flow associated with this diffeomorphism. It's simply we take N cross R and take F from N cross R to N cross R, taking F of xt into F of x t plus 1. So we take the cylinder, and this will be a proper free action if we take the quotient on this diffeomorphism, the orbits of this diffeomorphism, we get a manifold that fibers over the circle, and this is nothing else than the mapping torus of F. And this is provided with a canonical flow by obvious things, by R. And the flow has a phase return map, has a global cross section, and the phase return maps F. But there's a better way to do it, so instead of putting the additive structure here, we put the multiplicative, so this is R bullet, so this is to show you that I'm beginning to learn tech. So this is, okay, so instead of that, and then instead of doing that, we need to do for T positive, this still acts properly, you know, etc., etc., etc. And I take the quotient space, and it's the same thing. So I sort of took the logarithm of the exponential of the same. Why do I want to do that? Because I want to put here C star. Okay, so now let's start with the construction. So let lambda be a lattice. Okay, so as an additive group is simply set 4. Okay. Okay, so it's a discrete subgroup of C2 of maximum rank. And then of course we can take C2 by this lambda, and this is a complex T torus. Of course we are dimension 4, no? But okay, and we will denote it for simplicity as T lambda. Okay, notation T lambda. Okay? Now, here we'll make an assumption which is not always satisfied, and which is extremely interesting, is let phi from C2 to C2. You know, this think of it as a 2-1-1-1 complex version. We want the complex analog of a complex and also diffeomorphism, right? That's what we want. So let phi be a linear complex linear map such that, well, will be preserve the lattice. So this implies in particular the determinant of phi in absolute value is equal to 1, right? Preserve this lattice. Okay? So take that one. And there exists omega eigenvalue of this linear map such that omega is not of modulus 1. Okay? This already is an arithmetic problem which is extremely non-trivial. Okay? Because a complex map that has to preserve the lattice and has to have one complex direction which is fixed and which is dilated. I mean, in the real case, it's easy. In the complex case, complicated. In fact, it will imply, in particular, that such a thing exists. In fact, the complex torus is an abelian variety. It's an algebraic torus. Already strong restriction, and there's a final set of possibilities that I hope I have time to give you at the end. Okay, so you have that condition. So let y in situ be an eigenvalue, eigenvector corresponding to that eigenvalue, which exists by hypothesis. Okay, so we have that. Now, what's the analog of a complex torus? So we take first, we notice that phi induces, because it preserves the lattice, induces an holomorphism of a complex torus by complex multiplication. Right? So phi, because preserves the lattice, we go to the quotient and produce for you a holomorphic map from the torus to the torus. The torus thought of as a complex group, this holomorphism, a complex group. But this condition implies that this holomorphism is of infinite order. So for instance, it cannot come from any construction in algebraic geometry. You know, like holomorphism of an algebraic curve will induce the Jacobian holomorphism that will go to a finite order. So it's a little complicated. No? So one, this condition.
Excuse me, the condition of the eigenvalue that is expanding is there?
Or yeah, or if you take the inverse, different from one.
Yeah, so it's so this map is an also.
That's right. Yeah, and also in one direction. And the other eigenvalue will be automatically. So it's the analog of a complex and also. Precisely. Exactly. But the claim is that in the complex case, it's a little arithmetically complicated.
But it's actually an also in the real sense too.
Yes, absolutely. What won't be true is that the suspension will be an also. Because now in the complex you have one neutral direction.
Well, no, but the phi
This,
bar.
phi bar is an also. Yeah, absolutely.
The real sense.
Phi bar is a complex.
The complex map which is also.
And also, precisely.
And the splitting is
The splitting is by that one and the other eigenvalue, precisely. So it's the exact analog of a complex is super and also. What won't be true is that the thing that I will do will be an also flow. It will be an also flow if we modify the definition for a complex action. That is perfectly correct. So it is an also for it's a complex and also diffeom. And we want to suspend this anosoph to get an anosoph flow in the complex case. So how to do it? Well, we take. See, that's where I took the logarithm. Now you see why. Okay, and I take the map F, the clear map. So it's exactly an analogy with this one. In the first factor acts by the map, and on the second factor acts by dilation. Okay? So I claim now that the action of this F is free, proper, discontinuous, is everything. But you see, in the second factor we have to quotient C star by the homothetic transformation given by omega. Suppose omega is modulus greater than 1, it's a dilation. And so the quotient of C star by this homothetic transformation would be in fact an elliptic curve. These are tori, which are being moved. So think of this as the following: C star, so you remove the origin from C. And if you have the fibers are complex tori. So you take the fibers and contract them by, or dilate them, depending how you, if omega is less than 1, let's say. No? You contract it and you act on the fibers by this, and also complex and also diffeomorphism. You take the quotient, okay? So you divide this object. You get a complex tree manifold, called M. Not by gamma, but by F, sorry. I get M, complex tree manifold. And this manifold is beautiful because this manifold fibers over C star over gamma to the N. And so this is an elliptic curve. Has some moduli given by omega. And the fiber here is exactly the complex torus that we have. Right? And now the fact that Y is preserved produces to you in a canonical way an action. So why do I want that? Because I want not only to have this quotient manifold, but to have an action of the affine group. Okay? And the action is explicitly given in the following way. The following actions are complicated to write. Well, so what I do is I take the universal covering of this situation and everything commutes. So this will be universal covering of this, not the universal covering, the cover. This is covered by that, right? Via the lattice. So I will describe an action of the affine group here that commutes with F, and therefore the same action of the affine group. It's not useful because you see here that this will dilate, but just to write it properly, it will be so the action is on the right. So AB will act on XZ the following way. So this is an element of the affine group, and this is an element of C2 cross C, and this is the way the affine group acts on the point. Okay, everything works well, commutes with the action, and therefore this manifold M can be. Now I don't speak any language, because I had to learn French. Can be muni, no, can be provided. I don't even speak French, but can be gifted, no, can be what? Provided. Provided is okay. I'm losing all my language. So can be given an action of it. Can be given an action of the kind group. Okay. Now, if you use here a character of Z, you can twist this example. So these just twisted examples. Okay. Now the theorem says every action preserving a volume form is of this type. Theorem. Every locally free holomorphic action of this group on M3 with all the properties, compact, complex, etc., preserving a C0 volume form is of preceding type. It's any of those. So it's a complete list of all possible actions of the complex type. So you see, you have the second one is like solvable case, and the first one, PSL2C, is like semi-simple case, exactly an analogy. But something which is very interesting here is that unlike the real case, some of the latter examples are not homogeneous. Complex homogeneous. These examples. In fact, the condition for being homogeneous is that the determinant of E is exactly 1. Of the linear map that preserves the lattice must be necessarily of determinant equal to 1 to guarantee homogeneity. And this is due to the following fact. If this manifold M, the later case of suspension of a manifold fibering of an elliptic curve, was complex homogeneous, it will have a holomorphic 3 form coming from the Lie algebra. Therefore, its canonical bond will be holomorphic 3. And one can check that this is not always the case. Now, Etiennes has exploited this example to obtain a following beautiful thing: the existence of a complex manifold with a foliation by Riemann surfaces, each of which is of parabolic type, in fact, conformally C, but which cannot be given a metric that renders all its leaves flat. I mean, there's a theorem saying that, that if they were all hyperbolic in the sense of Kobayashi, then you can actually render every leaf hyperbolic. I'm sorry, of course, there's a metric continuous which renders every leaf of constant negative curvature. In this case, it's marvelous. You know, there's an obstruction which is very beautiful, and therefore it has to do with the simultaneous uniformization of leaves of affiliation. Okay? Before entering into details of the proof and the arithmetic, let me just mention how rich these examples are in some sense. Just one thing before I forget quickly. Here we can always make this manifold to be scalar. I mean, this manifold is scalar, so the base is scalar, but M not scalar. So it gives you examples of non-scalar manifolds which fiber of a scalar manifold, fiber scalar. Apparently it was an open problem, but somebody told me it's really easy if you consider Heisenberg complex groups. But I thought it was an open problem. Okay, so let's discuss a little bit about how rich the dynamics of this thing is. And okay, so let's consider the first case. So the first case was PSL2C divided by gamma. So this is the frame bundle. hyperbolic orbital. By definition, because an orbital has conic points, so what do I mean by frame model? That's what I mean. I mean, if instead of an orbital was a manifold, then it's reconciled with the frame model, or orthonormal frames. Okay, so this contains three vector fields. So let's recall the following. So the Lie algebra of C of the complex affine group is generated by two elements, x and y, right, satisfying the relation. So can always use generators of this two-dimensional complex Lie algebra to satisfy this relation, commutative relation, and therefore to have a locally free action. This implies that to have a holomorphic locally free action of the complex affine group on a holomorphic or on a complex free manifold is equivalent to what? It's equivalent to finding two holomorphic flows, holomorphic vector fields x and y, which are linearly independent at each point, and such that satisfy this relation. So the fundamental vector satisfies the relation. By this relation, as we work in a dynamical system, this relation can be restated in a more beautiful way.
Why do you need independence at each point?
Excuse me?
Why do you need independence at each point?
Because I want the action to be locally free.
Oh.
That's very important. Otherwise,
Okay.
Actually, it's a very good question that we plan to attack, but so far it's not so easy. So that's what I need, because I need the isotopic group to be discrete. Okay. Yeah. This is for this part. Otherwise, not important. So this relation here for dynamical system is the following: is if GT, capital T, the holomorphic flow, is the holomorphic flow obtained by integrating x, then it will satisfy the following relation. If we take its action on the vector field y, that's e to the t y. So this is the same thing as that one. Y is a vector field where gt is the flow, holomorphic flow of the first vector field. So that means that the vector field y on the differential is pushed by x, is not preserved, its direction is preserved, but is well, not expanded, depends on the real part of t, because t now is a complex number, is homothetically transformed into mod. So in particular, for instance, if the real part of t is negative, contracts, and you see why now it's not an also flow, because if t is purely imaginary, has a neutral direction. So that's what I hesitate a little bit, but you are totally correct. This is answer and also. But when you suspend the flow, you have to be a little careful, only with this small point, because there always will be a neutral path. Okay, so you have this. So you have this action. Okay, but it's fantastic because then we have, and of course I use G because this will be some sort of holomorphic geodesic flow. And I will use the letter H for the flow of Y, because it will be a complex holocyclic flow. So we have a, like that. And again, it's beautiful because, you see, this manifold therefore will be provided with two vector fields which are linearly independent, so that if you integrate the first one, the holocyclic, every orbit is dense. So, beautiful example of a complex manifold foliated with dense leaves, copies of C. And but you see, the geodesic flow now what will be its periodic orbits? Periodic orbits will be therefore quotients of C will be either C star or elliptic curves. Well, this will correspond exactly, you see, to this complex flow is sort of an extension of the geodesic flow. The geodesic flow is canonically defined essentially by parallel translation, and this is essentially defined by parallel translation of frames. Okay, so there will be an extra imaginary part here. And it's beautiful because, you see, this will, by the way, will preserve Haar measure. Because in PSL2C, the Haar measure is by and invariant on the left and the right. So we'll go down. So this will preserve a measure, a Haar measure. And this geodesic flow will have leaves, which are, or orbits, which are C's, copies of C stars, namely C divided by lambda, or elliptic curves. And so you have this, so the elliptic curves will be in a countable way, will be like geodesics, no? In the case of the geodesic flow. But now, for instance, so many ideas come to the mind. For instance, can we construct a sort of Selber like a zeta function? Because you see, there are ways of constructing dynamical systems, zeta functions, but take into account the periods of the periodic orbits. But now we have elliptic curves. And so why not combine the moduli? And so I've been trying to fabricate one, but I have to read several, something like that. But it's beautiful, no? Because, okay, so here's one problem construct, and in fact, for instance, if we allow this not to be compact, so suppose gamma is not compact at the lattice, that is PSL2, the Gaussian integers. And then in this case it's beautiful because you have some holocyclic orbits that are actually closed. And the invariant measure concentrated into that are fantastic and beautiful. I mean, it's related to Riemann hypothesis, to many beautiful things. The behavior of that, for instance. In other words, contains many. But this is just a parenthesis to show you that this is beautiful. You see, now, the Lie algebra of this consists of three vectors satisfying the same relations as before. And look at this. This is an example. So this is the frame bundle. So it's essentially an SO3 bundle over the orbital. So here you have this three-dimensional hyperbolic orbital, and the fiber is SO3, the frames. Okay, and you see, these two, Y and Z, generate a plane field, which is a contact form. So you have a beautiful analog, and these fibers will be transverse to the fibers. Like the unitangent bundle of a surface, the orthogonal planes form a contact structure, and therefore you can do Lagrangian geometry, Legendre curves, and you have a complex analog here in a really beautiful way by going back to the hyperbolic line. But anyhow, that has nothing to do, but a lot to do just to tell you how rich it is. Okay. Okay. I mean, of course, one gets in love with the things one does, no? But otherwise, we wouldn't do it. Okay, so this describes a complete set of invariants, etc. Okay. So how to prove such a thing? So I'll give you a sketch. Here you go. Okay. Just 5 minutes. In 5 minutes I tell you. It's very nice, the proof. But actually I will very quickly, okay, with my hands. And may I have a copy of the paper? Okay. No formulas, just... Okay. So x, y were linearly independent. Okay? That means that we have... that's right. That means that we have a foliation. So we have an hypothesis, we have an action. Locally free. Therefore, the orbits foliate n. Because it's locally free. So we have this three-dimensional manifold foliated by two-dimensional objects. It's holomorphic foliation. We observe that affine group has no compact quotients. Very easy, because this relation says that the volume grows, and you just cannot, it's incompatible. So no compact quotients. Okay, so what's the objective? If we were able to obtain a third vector field, linearly independent, okay, so this foliation contains two foliations. The ones the ones generated by x, and the one generated by y. So let me just write an individual leaf, and we match the foliations. So this is a copy of the affine group, and this is foliated by the holomorphic copies of C, and actually I should draw them like that. It's like separate like an also. The objective would be, the ideal would be, if I can manage to obtain a third vector field transverse to this leaf, such that in addition to the relation that I have, I would have so I'm almost close to the algebra. Can I do that? Automatically, from these relations, one obtains the third relation. Can we have that or not? Well, that's too hard to imagine. It's very difficult to obtain sections for vector fields. Now here is a three-dimensional. How can we expect to do that? Well, now, here is the only point in where we use the volume preserve. The action of the differential on vector fields is contracting. You see, along the leaves, the flow is dilating exponentially. Choose T to be real here. That's what the imaginary part doesn't bother. Okay, so think of this as a real.
T was what the...
T is a complex number.
X, that is the x time variable.
Yeah, that's right. G is for the x time. Now, if you take this real, you take the action on vector fields, the volume here grows exponentially, the area of the leaves. But I am requiring that a volume form be preserved. And that forces the transverse direction to be contracting. Now I have all the theorems of stable manifold theory to guarantee the existence of a foliation, the stable foliation. So first step, you know, the no pacing, but the standard pure Hadamard-Perron, sorry, Hadamard-Perron theorem. So I obtain a foliation, which is actually, each individual leaf is easy to see is holomorphic, is complex band. But otherwise the variation is, okay. Now we use the lambda lemma, because it's true that any codimension one foliation by complex things is automatically transverse to quasi-conformals. The lambda lemma, or holomorphic motions. So we obtain that, but now, you see, if we lay the holonomy along the action, it's obviously holomorphic, because the action is holomorphic. And therefore I'm forced to consider the holonomy along this direction. But we can prove that the two leaves are very close. They are, the holonomy of moving along that is 1 plus epsilon quasi-conformal. But now, to obtain any holonomy, we use the dynamics to bring them, where epsilon tends to 0 as the points get closer. We bring them very close with the dynamics, and therefore this would be quasi-conformal, 1 plus epsilon quasi-conformal for every epsilon. Okay? And therefore will be conformal. So first beautiful thing, this will be for us a holomorphic foliation, to begin to get very good, because we now obtain a third foliation, a second foliation, which is transverse. And then, because it's no time, then there's a dichotomy here, either something is integrable or not. If something is integrable, we get a solvable case, and if not, we take this case. And the most beautiful part, actually, I'm not giving, is the study of all 5 cases of, you see, of lattices that preserve, that have the property that there's an automorphism of infinite order. Is really beautiful. 5 arithmetic constructions, which are really nice. But a general problem we don't know how to solve is that one. If you give me a complex characterized complex tori of higher dimension, say dimension n, complex dimension n, that have the property that contain an automorphism of infinite order. Okay. I mean, one canonical example is if lambda is actually the direct sum of the same lattice. In this case, the automorphism of lambda is GL to Z. So in other words, if lambda is a product of 2 elliptic curves, no? Then the group of automorph is GL to Z, and this contains a free group of 2 elements, at least. A free group of rank 2, sorry. Not a billion free group of rank 2, and therefore contains infinitely many automorphisms of infinite orders. So like that, there are 5 examples. Okay, but I have a copy of the paper of 5.1. I can send it by email. Okay, finito. Sorry for the delay here.
Where does the number k appear in the construction? The k that...
The k, because there's a section.
Is that an invariant or
the number k, in fact, says that every action factorizes through ak for k even in the case of Pesel 2R, or in other words, the only actions of FAK, the covering of the coverings of the affine group, yeah, is if n is odd for SL2R. If n is even, you have actions of that. In other words, any action factorizes to. Let me read. I forgot at the moment. If one is even, one is odd. Don't remember. See, essentially, any holomorphic action which is locally free and volume preserving a compact complex demand factors through affine K. That's what I want to say. For some finite integer k, and is holomorphic conjugate to one of the examples.
I was asking about what the meaning of this number.
This case, it's a little. I mean, you see, if this vector field y. Suppose I don't get a vector field y which is invariant into the floor, but such that comes back in finite time. That's the meaning of k. So there's an ambiguity. Sorry. In other words, you cannot trivialize this bundle, but up to a finite cover you can trivialize it holomorphic. That's the meaning. But so this, if you want, this belongs to the realm of holomorphic anosoplos. Exactly, holomorphic anosoph behavior in dimension 3. For higher dimension, I do think let's hope. This is a complete analog of the cases. Copy. No, it wasn't copy. And no Dennis won't be watching. You turn it off.
No.
I know you.